Alrighty, Bulldogs. We just learned how to use the power rule to find a derivative instead of the formal definition of a derivative. Today we're going to learn two more different rules for finding derivatives. So we know the power rule only works when you have a variable raised to a power. So what happens when we are looking at a product of expressions or a quotient of expressions? Now, both of these examples can be done using the power rule. But then I'm going to show you how we could also do them using what we call the product rule and a quotient rule, and you'll see you get the same answer. So you've got some options on how you want to work some of these problems. So let's say I just wanted to differentiate A with the power rule, excuse me. I know that I need this to be in the form of a polynomial, so I'm going to just rewrite this first, and I'm going to distribute out my two binomials. So we'd have 6x squared plus 10x minus 12x minus 20. So 6x squared minus 2x minus 20. And when we take our derivative, using the power rule, 2 times 6 is 12. X squared drops down to x. 1 times negative 2 is negative 2. X to the 1 drops to x to the 0, so we don't have a variable left. And then the derivative of a constant is 0. Okay, so this is the derivative of f. So let's take a look at this product rule. So you can use the product rule when you have the product of two expressions. And so I'm going to call this the first expression and g of x the second expression. So the shortcut to finding the product rule is we're going to take the first expression times the derivative of the second plus the second expression times the derivative of the first. So if we take a look at example number 1, it's the same exact problem we did up here. This is my first expression, this is my second expression. And I'm going straight to the derivative, no rewrite necessary. So first expression, 2x minus 4, times the derivative of the second. So the derivative of 3x plus 5 would just be 3, plus the second expression, which is 3x plus 5, times the derivative of the first, which is 2. And then I'm just going to clean this up a little bit. So distribute your 3, distribute your 2, and add like terms. And we're left with 12x minus 2. Sure enough, that is the exact same, sorry about that, that is the exact same derivative that we had up here. Okay, so you now have one option is you can distribute everything out and just use the power rule, or you can keep it in a multiplied form and you can apply your product rule. So at this point in our curriculum, almost everything we're looking at could be done with the power rule, but very soon, as in the next section, 3.5, we're going to learn about trigonometry derivatives, trigonometric derivatives, and we won't have that option anymore. So we will absolutely rely on the product rule soon. Okay, so another rule that we will find very helpful is the quotient rule. And again, I'm going to show this first by using my power rule, which doesn't always work, but sometimes it can absolutely be faster. So on part B, we have an expression where your denominator is just a single monomial, which means if I wanted to, I could rewrite this, dividing both of my terms by the denominator. Now, I don't have that ability if I'm looking at an expression like number 4, where I have a binomial on the bottom. We can't divide these individually and get a polynomial left. So this technique of rewriting and applying my power rule only works when you have a monomial on the bottom. So negative 10x to the fifth divided by 2x cubed is going to be negative 5x squared. And then 3x squared divided by 2x cubed. 3 divided by 2 is 3 halves. And x squared over x cubed leaves you with a 1 over x. So I'm going to push that x up to the top. So we would have an x to the negative 1. Okay, now I'm going to find my derivative using my power rule. So 2 times negative 5 is negative 10. X to the 1 power. Negative 1 times 3 halves is minus 3 halves, x to the negative 2 power. And I'm just going to rewrite this And I'm going to bring this x to the negative 2 down to the denominator so that my final answer is written with only positive exponents. Okay, so I'm now going to take the exact same problem and I'm going to apply this new rule called the quotient rule. So what does the quotient rule say? It says if we are trying to find the derivative of an expression divided by an expression, we can do this. So this is the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function all over the bottom function squared. And when I was in school, way back in the day, my calculus professor had a little kind of, not a rhyme, but just a little way to remember this. So he used to say low d high minus high d low over low squared. And it just stuck for me. So low means you use the bottom function times the derivative of the high function minus the high function times the derivative of the low function all over the low function squared. So you're going to hear me say low d high minus high d low over low squared a lot. So if we look at example number 2, there's no need for a rewrite because you are not going to be needing to use the power rule. So I'm just going to dive straight into my derivative. So low d high, so low is 2x cubed. D high, so derivative of the top, so that would be negative 50 x to the 4th plus 6x minus high d low. So the high function would be negative 10 x to the 5th plus 3x squared d low. So derivative of the bottom would be 6x squared. And that is all over low squared, so 2x cubed squared. And now we're going to just clean this up. So distribute your 2x cubed, we would have negative 100 x to the 7th plus 12 x to the 4th. And I'm not going to distribute a subtraction symbol and the 6x squared in my head at the same time. So what I like to do is either distribute that subtraction symbol to the first expression or to the second one. I'm going to distribute it to the second one only. And now I'm going to distribute that. So we would have plus 60x to the 7th minus 18x to the 5th. Oh, I'm sorry, x to the 4th. And that is all over. And when you square this expression, the 2 is squared, and then x cubed squared is x to the 6th. So now I'm going to clean up my terms. Negative 100x to the 7th plus 60x to the 7th is negative 40x to the 7th. 12x to the 4th minus 18x to the 4th is negative 6x to the 4th. And that is all over 4x to the 6th. Now you might be looking at these and saying, wait a second. Oh my goodness, I'm so sorry you couldn't see what I was doing. You might be looking at this and saying, well, those aren't the same answer. Well, actually they are. If you were to divide this out, negative 40x to the 7th divided by 4x to the 6th, that's going to give you negative 10x. There's my negative 10x. And then 6x to the 4th over 4x to the 6th. 6 over 4 leaves you with 3 over 2. And that would leave me with an x squared on the bottom. So these are equivalent expressions. And you're probably looking at this and saying, why in the world would I want to use this process if I can use the power rule instead? And I agree with you completely. So I always look for, if a problem has a monomial on the bottom, I divide it out and I apply the power rule. But sometimes you don't have that option. And your only choice is to use the quotient rule. All right, let's take a look at another example. Let's look at example number 3. So we're going to find the derivative, and I do not have the option of using the power rule here. So we're going to do low d high minus high d low over low squared. So low would be 4x minus 2. D high, derivative of 3x minus 1 is 3. Minus high, which is 3x minus 1. D low, which is 4. All over low squared. And I'm just going to clean that up. So 12x minus 6. I'm going to take this negative and I'm just going to apply it to the negative 4 and then distribute my negative 4. So minus 12x plus 4 all over. And there is no need to expand this out. you can keep this in a nice factored form. So one more step to clean this up. 12x minus 12x cancels. Negative 6 plus 4 is negative 2 over 4x minus 2 quantity squared. Okay. I'm going to skip over example number 4, but I do want to show example number 5 because we got radicals in there. And so this is where it starts to get a little bit ugly. All right, so what we're going to do, before I apply my quotient rule, I am going to rewrite the numerator and denominator so that we have a 1/2 power instead. Even though I'm not applying my power rule, I know that during the quotient rule I have to take derivatives, and it will be easier to take a derivative if it's in the correct form in order to apply a power rule. All right, so now I'm going to start my quotient rule. So low d high minus high d low over low squared. So low is x to the 1/2 minus 1. D high, so that would be 1/2 x to the negative 1/2 minus high, which is x to the 1/2 plus 1, d low. So that's 1/2 x to the negative 1/2 all over low squared. And we're going to clean this up. So I'm going to distribute here. So 1/2 times 1 is 1/2. X to the 1/2 times x to the negative 1/2. You are adding the powers, and 1/2 plus negative 1/2 is 0. So you have x to the 0. So you actually don't have a variable left there. Minus 1/2 x to the negative 1/2. Over here, I'm going to apply or distribute this negative to the second expression and now distribute here. So we would have negative 1/2 times 1 is negative 1/2. X to the 1/2 times x to the negative 1/2. Those powers add to 0. So x to the 0 is 1. And then negative 1/2 times 1 is negative 1/2. X to the negative 1/2. Oops, there we go. And that is all over x to the 1/2 minus 1 quantity squared. Okay, so let's clean this up some more. So I'm seeing that my 1/2s are going to cancel out. So 1/2 minus 1/2, that's gone. Negative 1/2 minus 1/2 is negative 1 x to the negative 1/2 over x to the 1/2 minus 1 squared. Okay, so this looks like I'm done, but we typically do not want to see positive exponents or rational exponents. So I am just going to rewrite this. And the first thing, I'm going to move this to the denominator. Now, if this were attached to any other terms, I could not do that, but it's just a singular term, a monomial up there. So I'm allowed to rewrite that as 1 over the square root of x multiplied by the reciprocal. The faster way to do that is we can just push that into the denominator. And then x to the 1/2 on the bottom is the same as the square root of x. And then over here, I'm going to rewrite x to the 1/2 as square root of x. Don't try to get fancy and distribute in here. We're not allowed to do that because we have an exponent, and exponents always occur before multiplication. That's just our order of operations. Okay, so this is a good stopping point. Now we do have one final component to the Chapter 3 video series, and these are some more challenging problems using the power rule, product rule, and quotient rule, but I'm going to save that for another video. So now you've got 3 of the very important derivative rules that we are going to use throughout the course. Thank you so much for listening. Good luck.